So good evening everyone. Today we will start with the electromagnetic radiation and absorption spectroscopy. Okay. So coming to the electromagnetic radiations, which are also regarded as in short they are regarded as EMR. So what are they? So EMRs are basically synchronized oscillation of electric and magnetic fields. Okay, so they are the synchronized oscillations of electric and magnetic fields. Okay, so EMR, they are also regarded as transverse waves. Sorry, my hands are freezing, so my writing is a bit wonky. So please excuse me for that. Yeah. So these are also regarded as transverse waves. So what are transverse waves? Can anyone let me know? No? Okay. So suppose we have a pond. Okay. And in the pond, I throw a stone. So you will find some ripples. They are being generated, and these ripples, they are moving outwards away from the point of the disturbance while you have thrown the stone into the pond. From that point, these ripples are moving outwards. Okay. Further, at any given point of time, you will see that there is a formation of a higher point and a lower point in the waves. Okay, so these waves, they are moving in a straight line, and also they are creating disturbance at a perpendicular directions. Okay, suppose if our plane, this pond plane, it is in the x and the y direction, then we will also find a disturbance in the z axis. So if you see, basically we are having two types of waves, one which is moving in the xy plane and another which is showing some amplitude variations in the z directions, and both of these waves or the signals, whatever you say, they are perpendicular to each other. Right? So if there are two kinds of waves which are moving synchronously and at the same time they are perpendicular to each other, they are regarded as transverse waves. And EMR, if you see that if the vertical direction, it is the x direction, and the horizontal direction over here, it is the y direction, and the propagation direction is the z axis. So we have x axis, y axis and z axis. So if you see in the x axis, our say this blue line, it is the electrical vector. So it is moving in the x direction. The magnetic field, it is moving along with the electrical field, but it is moving in another plane which is perpendicular to the electric field, and we are getting that magnetic fields. So both the electric field and the magnetic field, they are moving together. However, both these fields are perpendicular to each other. Hence, the electromagnetic radiations, they are also regarded as transverse waves. Okay. Now herein, what are the examples of the electromagnetic radiations? The examples includes the radio waves, microwaves, infrared waves, visible light. They are also electromagnetic radiations. Then we have ultraviolet rays, we have X-rays, and we have gamma rays. Okay. The electromagnetic radiations or the electromagnetic waves, they carry energy, momentum, and angular momentum from the source to a particular direction, and that direction we call it as the polarized the polarized direction or the propagation direction. So that means electromagnetic waves or the radiations, they carry energy, momentum, and angular momentum along the propagation direction until they interact with some matter. Okay. So what I said, these electromagnetic radiations, they are moving in a particular direction, which I called it as the propagation direction, and while it is moving, at some point of time it will interact with a matter. Okay. Now when it is interacting with the matter, these EMRs, they would impart the above quantities to the matter. Okay. So that means it will transfer some energy, some momentum, some angular momentum. So it will give some of these what you call energies or the parameters to the matter. Okay. And how this interaction takes place? Interaction means the interaction between the EMR and the matter. The analysis of this interaction, it is explored in the spectroscopy. Okay. So what is spectroscopy? Spectroscopy is nothing but the analysis of the interaction of the electromagnetic radiations and the matter. Okay. Now, when we look into the electromagnetic spectrum, so if you see on the left hand side, we have gamma rays. Okay. Then we have X-rays. As we move towards our right, we have X-rays, we have UV. Then we have the visible spectrum. Within the visible spectrum, we have Vibgyor region, so which moves from say 380 to 750 nanometer wavelength. Then we enter into IR, then we enter into microwave, then we enter into the radio waves. In the radio waves, we have FM and the AM ranges, frequency modulation and amplitude modulation ranges, and then we have long radio waves. If you see, as we move from the left to the right, there is an increase in the wavelength. Okay. On the other hand, we all know that wavelength, it is inversely related to the frequency. So when we are having low wavelength, we'll be having high frequency. So as we move from left to right, the frequency would start to decrease. Okay. Yeah, the frequency would start to decrease. Now, what is happening over here? what would happen? Say in the gamma ray region, suppose you are having say 1 unit length, say 1 second. Then you have X-ray region. So you are again having a 1 second band. So what would happen? In the gamma rays, if you remember correctly, if you see, we have shown this electrical field in a sinusoidal fashion. Okay. So we are just not considering the electrical field at this moment, and we are thinking that the what do you call the magnetic field, it is non-existent, just for the sake of the understanding. Okay. So over here, within this 1 second period, the number of these sinusoids, that means the period of the sinusoid, not the sinusoid, the period of the sinusoid would be greater in the case of the gamma rays as compared to the X-rays. So there will be lesser cycle. So this time period T would be A. So the cycle, the time period would be greater. So your number of the cycles would be less. Okay. So here period is smaller. And we have higher number of cycles of the sinusoids, and in the second case we will be having lower number of cycles of the sinusoids. Okay, so what does this mean? What are these sinusoids? So these sinusoids, they are nothing but they carry packet of energies. So if you want to find out the length of the sinusoid waves, it would be higher in the case of gamma rays. So that means the packet of energies in the gamma rays will also be higher as compared to the X-rays. So what does this indicate? This indicate as we move from left to right, the frequency is decreasing, and as the frequency is decreasing, the packet of energies per unit time carried by the electromagnetic radiations, they are decreasing. Okay. Now since they are decreasing, that means they would become more and more non-lethal in nature. Okay. So when I say non-lethal in nature, suppose you are here, you are standing over here, and there is a kid who runs into you and both of you get banged. Will this kid create any damage to yourself? No, you may get some injury, but that would be non-lethal, or it would not be a major injury. However, you consider that there is a big fat man. There is a big fat man. Okay. He is running at the same speed and he bangs you while running. So he is carrying higher momentum than the smaller kid. So the chances of getting injured is much higher. So the impact will be much higher because he is carrying the big fat man. He is carrying a larger momentum. Interacting with you, impact means nothing but it is an interaction between the two persons. So when he is interacting with you, the transfer of energy would be much higher. Okay, and the chances of injury will be quite high. Okay. Now this is in the macroscopic scale. Okay. But we are discussing over here about the packet of energies which are minuscule in size. Okay. So what would happen? I will give you another simple example. Another simple what do you call interaction example. Suppose all of you, I hope all of you eat chapatis, right? And all of you know how to make a dough. So you have made a dough. So this is a dough surface. I give you a small ball bearing. What would happen? And I ask you to throw it from the top. You just release it. It will go and it will sit on the top of the dough. If you use a bigger ball and you release it from there, what would happen? It will dent, it will create a dent onto the dough surface and it will sit inside it. And if you again further increase this ball size, it may penetrate through the hole of the dough and it will gain entry to the bottom, right? So over here also, if you consider the gamma rays, they have sufficient energies to pass through your body. Okay. Similarly, X-rays also, they have sufficient energies. If they are made incident onto your human body, the X-rays will also be passing through the body. And this property of the gamma rays and the X-rays to pass through your body, because why they are passing through your bodies? They are passing through your bodies because they are having high energy. And because of that, they are carrying a lot of energy. They can overcome some of the frictions which is being exerted by our human body. Okay, and there will be some gamma photons or the X-ray photons which will reach the other side. And due to this reason, these gamma rays and the X-rays, they are being used in medical imaging. Are you getting my point? However, if you go towards these radio waves, by the time you reach the radio waves, we all listen to radio. Do they create any, do they pass through our body? No. And due to this reason, our ultrasound waves, they are used to detect any matter, whether suppose you are having an ultrasonic source and you bring an object over here, it will go strike and it will come back, and from there you can find out whether there are any obstacle in front of you or not. This obstacle may be a human body, may not be a human body, and in this way you are able to detect the presence of a matter in a non-destructive way. The non-destructive way means it will not create any harm to the human body also. And these ultrasonic ultrasound generators, they can be easily used for human imaging and all these things, right? Now, among this region, there is a specific region which is of utmost importance, and that region is UV visible and infrared. So what happens is that the radiations in this region, they are very commonly, I am not saying only that these radiations are used, I am saying very commonly. Okay, so these radiations, UV, visible and the infrared radiations, they are very commonly used in spectroscopy. And in most of the labs, you will definitely find UV visible spectroscope. Okay, most of the biological labs. You will find UV vis spectroscope. Okay, then you will also find IR spectroscopes also, but this is not very common in most of the labs because the cost of this IR instrument is quite high due to the higher price. This kind of spectroscope, IR spectroscope, you will not find much. Okay. The cost of a typical spectroscope, it starts, if you want to go for a single beam spectroscope, it starts with rupees 1 lakh, 1 to 1.5 lakh. In 1.5 lakhs, you can get a somewhat good spectrophotometer just to do normal routine day-to-day activity, but not of the research yet. But if you are willing to spend approximately 2.5 to 3 lakhs, you can get a good UV visible spectroscope. Okay. However, on the contrary, if you want to buy an IR spectroscope, it would cost you at a minimum of 12 to 15 lakhs. This is the minimum price, 12 to 15 lakhs. So you will find that this IR spectroscope, they are not much common in most of the biological labs, and they are available only in some of the bigger labs. Okay. So here again in the UV visible spectrum, if you see the wavelength starts from 380 and it ends at 750. Okay. And in the UV region, usually we look into this the general UV visible spectroscopes. They function in the range of 280 to 380. Okay. And for the typical UV visible spectroscope, you will be having 280 to 750, and somewhat in the near IR region also you will get. So not much, but in the wavelength range of 280 to 800 nanometers. Okay. Now over here, if you see in this chart, and given the range of frequencies, that means the spectrum of the electromagnetic radiations and their respective wavelengths and photon energies. Okay. So in the first class, these are the classes. And what are the radiations? We have gamma rays, then we have hard X-rays, then we have soft X-rays, and then we have extreme ultraviolet rays. These rays or these electromagnetic radiations, they are called ionizing radiations. Now, why they are called ionizing radiations? We all know all matters, they are basically made up of atoms. So they will be having some orbitals, and within that orbitals you will be having some electrons which are moving on their own, and they are happily moving, right? Now if you make an ionizing radiation incident over here, now this ionizing radiation, in short I am saying as IR, this is not infrared ionizing radiation, okay. So what it can do, it can strike off this electron from its place. And when it is striking off this electron, this atom is losing one electron. Okay. So atoms are neutral because there are equal number of electrons and the protons. Now, since you have knocked off one of the electrons, what you have done? You have made this atom a charged atom, or we can say that we have ionized the atom. Okay. And these radiations, whether it is gamma rays, whether it is hard X-rays, whether it is soft X-rays, whether it is extreme ultraviolet X-rays, they are all ionizing radiations. They are all ionizing radiation. Okay. So that means these radiations, they have the capability to alter the atomic architecture, okay, and make them ionize. And ionization is not a very good thing. It can lead to various diseases, which includes cancer. Okay. Now there are the second category. It is the near ultraviolet, near infrared, mid infrared and far infrared. So these radiations are there and they are quite useful. However, still what I would say is that in the near ultraviolet radiation, if you see if there is any ultraviolet radiations, they appear as purple colored. Purple colored light. Okay. It is around in the region of say around 380 or somewhat. This you will find that uh, there are some UV radiation, UV lights which are what you call, which are giving light in the range of this 380 nanometer and so. Okay, even under these UV radiations, please be advised, don't enter into the room while the UV light is on, because even though we are talking about near ultraviolet light and they are non-ionizing radiation, if you take this radiation for a very high time, it can cause injury to your tissues. Okay, it can cause injury to your tissues. Okay, then we have infrared lights, mid infrared lights and far infrared lights. Then thereafter we have this microwaves and radio waves. So we have this extremely high frequency, super high frequency, ultra high frequency, and so on. Medium frequency, low frequency, very low frequency, ultra low frequency, super low frequency, and extremely low frequency. Okay, so these are the microwaves and the radio waves. Okay, and their corresponding frequency and wavelength are given. If you see, the wavelength is increasing, however, the frequency is decreasing. And if you see the energy per photon, it is directly, energy is directly proportional to the frequency. So at higher frequency, we have higher energies. Okay, and as we are going down, there is a decrease in the energy levels. Now talking about the spectroscopic types, There are 5 types of electromagnetic radiations which are usually used in spectroscopy. The first one is the X-ray. The second one is ultraviolet and visible spectroscopy. Then third one is the infrared, microwave, radio waves. So when we are using X-ray, then the spectroscopy is regarded as X-ray absorption spectroscopy. When we are talking about ultraviolet visible, when you are using ultraviolet visible light, then we call it UV vis absorption spectroscopy. Then if we use infrared, it is called IR absorption spectroscopy. If we use microwave, then we call microwave absorption spectroscopy. And if we use radio waves, we can have electron spin resonance spectroscopy and nuclear magnetic resonance spectroscopy. Now, coming to the basics of spectroscopy. Absorption. What do you mean by absorption? It is basically transfer of energy from the electromagnetic radiation to a molecule. Okay. Over here, I will take the same example as that of the somewhat previously I told you that you are standing somewhere and a kid, he comes running to you, he bangs you. When he is interacting with you, you will find that you are moving slightly backwards to absorb the shock from the kid. Okay. So what you are doing? You are absorbing the total energy of the kid into yourself by moving slightly backward. It is not that you are intentionally doing, but when the kid strikes you, you automatically go backwards because you are then absorbing the energy. Your body is absorbing the energy from the kid. Okay. So here the absorption is total absorption of the energy. But this is not of use for us. This kind of thing where complete absorption is happening, it is not in our interest. So what we have basically in a basic spectroscopy, in a basic spectroscope, we have a light source. We have a light source. Okay. Then we have some matter. Now this light source, it is emitting some EMR. Say it is emitting 100 photons. This 100 photon, it is interacting with the matter and then it is coming out from the other side of the matter, and then there is a detector DR which is detecting the electron. Now, as I told you, we started with 100 photons, and herein, say some photons, say 20 photons, they are getting absorbed by this matter, and on the other side we get 80 photons, and these 80 photons is being detected over here. Now herein, if you see, I have told that I have used a light source. Now whenever a radiation source is used, it is a wideband source. What do you mean by wideband source? Wideband source means there are radiations of different frequencies. Okay, and when you have different frequencies of EMR, then it is called polychromatic source. Okay. Now herein I will take an example of a small family. Say there are 4 people, A, B, C, and D. Okay. And they go to their relative's house. Say the relative is E. Now it might be so possible if we consider the whole family and say they go to the relative's house over here, and then we are trying to analyze how this family behaves with or interacts with the person E. If you see, if A is interacting very positively, say he's interacting, if we give it some number, say it interacts with E on a scale of 0 to 10, he interacts in a way of 7. B, he or she interacts with an interaction point of 5, 3, 1. But if you have to look into the interaction for the whole family, you have to find out an average of this one, and you will get an average interaction. You are not getting specific interaction. However, if there is a way that if we can analyze the interaction of A separately, B separately, C separately, and D separately, then we will be able to understand how these individual members they are interacting with the E in a manner. So you will get an independent analysis, member dependent independent analysis, and which might be quite helpful in creating a product or coming out to a common platform. The same thing happens over here also. When you are using a light source, as I said, all the light source or the electromagnetic radiation sources, they are wideband source and they are having they are regarded as the polychromatic source. So yeah, definitely they will give you some results, but those results will be an average of the interaction of each of the frequency components of the given radiation source or the radiation which is coming out of the light or the source, right? Now what to be done? The thing is that we convert this polychromatic source into a monochromatic source using different mechanisms. One is we can apply prism. If we are talking in the case of visible light, we can use prism. We can use specific filters. Okay. We can use diffractometers. So what does this do? From your class 12 example, you can say that when we pass a light from any of these, they will break down the light components, right? So when they are breaking down the light components, what are those? You are basically getting or narrowing the frequency component of the light sources, and from here you can use each of these light sources by using specific components, and you can harp these lights which are monochromatic lights. We call it a monochromatic light, but again it is not possible to get a specifically a very specifically a single wavelength, but using very specialized equipment we can reduce the bandwidth of the lights of the electromagnetic radiation, and we can get a very small band, and which we can assume it as a monochromatic light. And then over the frequency spectrum, say 400 to 800 nanometer, at various wavelengths, say 400, then 401, and so on up to 800, at each and every wavelength you will be able to analyze the interaction between the electromagnetic radiation and the matter. Okay. Now, if you see in the absorption spectroscopy, I have written lines of patterns. What are these? These are nothing but when you're analyzing the matter in the presence of when you are analyzing the matter through the wavelength. So across the wavelength, so say it is 400 to 800 nanometer. So this is the wavelength band. Then you are scanning. There is no interaction. Suppose there is a wavelength where the matter, it absorbs the light. So at that wavelength you will get a line. Again, as you move from that wavelength, you will again get a bright spot, and slowly as you move towards another wavelength, you may get another line. Again, as you go towards the 800, you may get another line and another line, and these lines, whatever you are getting where the maximum absorption is happening, they are called the lines of patterns. And these lines of patterns are basically due to the absorption of the specific wavelength electromagnetic radiations by the functional groups which are present in the chemical structure of the matter. Okay, and accordingly they are used. These lines of patterns, they are used for the functional group identification and the chemical structure determination. Okay. So what happens over here basically, if you look into the electronic diagram, the absorption spectroscopy is something like this. You have the electron in the ground state. You have this photon which is going and striking over here. It moves this electron to the A2 level, and you will be getting the residual photon H of mu1, say. Now this mu1 is being detected. How much there is a so there will be a, if you consider that there is here say, because electronic levels have been given as E1 and E2, say the energy is given as P1 and over here the energy is given by P2. So by calculating the difference between this thing, the delta P, which is the delta energy between the incident and the light which has passed through, we can find out how much of the energy has been absorbed by this electron to go to the excited state, and we basically find out that thing. And this is absorption spectroscopy. Okay, this is the basic principle of the absorption spectroscopy. On the other hand, in emission spectroscopy, what happens? If you see, it says the internal energy of the molecule is converted to the electromagnetic radiation. Okay. Over here, what it says, suppose we have excited this atom, oh no, sorry, the electron, it has gone to the excited state. Now it stays over there for some time, and after some time we come over here, this electron, it comes down to its ground state, and while coming down to the ground state, it releases an energy, because over here it is at a higher energy, and when it tries to come down to the lower energy level, it releases that extra energy, and that extra energy is being detected. Okay. Now in that case, you will see that in emission spectroscopy, we are basically having both this activity. First absorption is happening and then emission is happening, but we are only interested in the emission spectra. So what happens, somehow whatever the residual light which comes out of this absorption interaction, that is being blocked, and we only record this emission spectrum. And due to this reason, since there is no radiation source as such which is illuminating the detector, again 400 to 800, I am taking the example, this platform is dark. Okay, and over there we will be getting some bright spots. We will be getting some bright spots or the line of patterns which will give us an indication about the functional groups. On the contrary, in the absorption spectroscopy, the background is bright. Okay, background is bright and we get dark lines. Whereas in the emission spectroscopy, we have dark background and bright lights. Are you getting my point? So I hope you have understood what is emission spectroscopy. Now coming to the internal energy level. So we have initially the ground energy level. So over there we have rotational energy, vibrational energy, and electronic energy. So that ground energy level, it is given by Eg, which is equal to the summation of energy of rotational energy, energy of the vibration, and energy due to the electronic energy. When wavelength of natural frequencies strike a molecule, so over here I am saying natural frequencies. Natural frequencies is the frequency where there is a specific liking of the photon by the matter. So due to which you are getting these lines of patterns. Okay. So when wavelength of natural frequencies strike a molecule, the molecule is then raised to the excited state. So that means this h mu, what is this h mu? H mu is nothing but energy. When the energy of this one and this electron will match, then only it will go to the excited state, and that's why you would get this specific lines of patterns. Okay, until and unless this energy and this energy of this electron, they do not match, it will not go to the excited state. Okay. So the delta E over here, it is usually, it has been found that it is 286,000 kilocal per mole. Okay. Molecules in general, it returns to the ground state within a time of 10 to the power minus 9 to 10 to the power minus 8 seconds, and while doing so they releases their energy. Okay. This is the schematic energy level diagram. So you are having the rotational energy levels, then you are having this vibrational energy levels, these bigger ones. Then you are having this in the excited energy state, electronic state, you have rotational energies, vibrational energies also. Then diagram showing electronic transitions. Different types of transitions have been shown. So we are having basically electrons like sigma electrons, which are bonding electrons, pi electrons, which are bonding electrons, and n electrons, non-bonding electrons. Similarly, in the excited state, we have anti-bonding and this pi star and sigma star uh, electrons, anti-bonding this thing. So over here, what you get? We get n to pi star transition. We can get pi to pi star transition. We can get n to pi star transitions. Then we can get pi to sigma star transition. Then we can get sigma to pi star transition. However, these two transitions, pi to sigma stars and sigma to pi stars, though they are theoretically possible, however, these are forbidden transitions. These are forbidden transitions. Practically, they are not occurring. Okay. Then lastly, we have sigma to sigma star transitions, and as we go from left to right, you will find that there is an increase in the energy which is required to cause these electronic transitions. Okay. Then types of electrons. What are the types of electrons is there? They usually do not show absorption in the UV region. In some cases, sigma to pi star transition it results in the hyper conjugations, and they are usually found in fully saturated systems, sigma electrons. Then n non-bonding electrons, they are present as lone pairs in nitrogen, oxygen, sulfur, and halogen, and it shows n to pi star transitions in the UV region. Then we have pi electrons, so which are basically the mobile electrons, and they are found in unsaturated compounds in multiple bonds, and they result in pi to pi star transitions in the UV visible region. Then absorption spectrum. I have already told you how does an absorption spectrum it looks like. You will get a when you do the scanning, you will get a bright background, and over there you will be having some lines. Okay, say 400 to 800 nanometer. Chromophore, it is a functional group which absorbs visible and the wavelengths, and because of this chromophore we get this whatever, sorry, I have drawn the wrong arrow. So we get this lines of patterns. So depending upon the nature of the chromophore, you will be getting the patterns. Then oxochrome. What are oxochromes? They are also the functional groups. Now, if they are present within the molecule where you have the chromophore, they may either shift these lines either to the higher wavelength or to a lower wavelength, or they can increase the intensity of this absorption spectra of this line. Okay, same, they may alter the absorption characteristics basically. So they are called oxochromes, and they do not basically absorb radiation at wavelengths greater than 200 nanometer, but they modify and shift the absorption bands of the chromophores. And then we have this spectral shifts which is occurring. So these are the different types of chromophores which are there. Then what are the systems? Then examples of this one, you need to remember this table. you may get some questions from here. Okay, so what are the maximum wavelength at which they can show some absorption bands? These are some what do you call? You may get instead of 165, you may get it at 167 also, depending upon what oxochromes, if they are present or not. Also, in what solvent you have dissolved your uh, substance or the molecules. Depending upon that, there might be slight variations, and these are the electronic variations which are responsible for the absorption band. Then shift. There are four types of shift. If it is happening in the wavelength scale, that means if it is happening at a higher wavelength, suppose uh, your normal chromophore, it absorbs at say 480 nanometer, and after you have done the chemical modification of a compound, it moves to 500. Then it is moving towards the higher wavelength, higher wavelength, and then it is called red shift or bathochromic shift. If it is moving towards the lower side, say 460 nanometer, then it is called hypsochromic shift or blue shift. Okay, and if the absorption is increased, suppose usually we measure it in the form of 0 to 100% absorption. So suppose your present absorption is at say 80%. If it increases to say 90%, then we call it hyperchromic shift. And if the outcome reduces the absorption to 70 or so, then we call it hypochromic shift. Okay, so these are four kinds of shifts which you need to remember. Bathochromic shift, which is red shift; hypsochromic shift, it is blue shift; hyperchromic shift, where there is an increase in the absorption; and hypochromic shift, when there is a decrease in the absorption. Okay. Conclude the chapter. If you have any questions, I will be happy to answer. No one is having any question?
No, sir.
Good.